How to prevent deadlocks in advanced debugging. Have you ever faced a situation where your program just stops working and you can't figure out why? This frustrating scenario is often caused by deadlocks, especially in programs that use multiple threads. Let's break down how to prevent these deadlocks in advanced debugging. First, it is essential to understand the conditions that lead to deadlocks. There are four main conditions: mutual exclusion, hold and wait, no preemption, and circular wait. If all these conditions are present at the same time, a deadlock can occur. To prevent deadlocks, you need to break at least one of these conditions. One effective strategy is to use consistent lock ordering. By establishing a strict order for acquiring locks, you can avoid circular wait situations. For example, if thread A always locks resource 1 before resource 2, and thread B follows the same order, they will not block each other. Another tip is to minimize the scope and duration of locks. Keep the critical sections of your code as short as possible. The less time a thread holds a lock, the lower the chances of other threads getting blocked and causing a deadlock. You can also implement deadlock avoidance algorithms. The banker's algorithm is a well-known method that checks resource requests before granting them. This ensures that the system remains in a safe state, preventing deadlocks from happening in the first place. Timeouts and retry mechanisms are also helpful. By setting a time limit for acquiring locks, you can avoid indefinite waiting. If a thread cannot get a lock within the specified time, it releases any held resources and tries again later. This can break potential deadlock cycles. Using advanced concurrency mechanisms can further reduce the risk of deadlocks. Lock-free data structures and transactional memory are examples of tools that manage concurrent access more safely. These modern approaches help you avoid traditional locks, which are often the source of deadlocks. Monitoring and detecting deadlocks dynamically is another smart move. By integrating runtime monitoring tools, you can analyze thread states and resource allocation. This allows you to catch deadlock conditions early, making it easier to diagnose the problem. Lastly, specialized debugging tools can be a game changer. Advanced debuggers come with features that help identify subtle deadlock scenarios. For instance, they can automatically capture thread states when performance drops or deadlocks occur, providing you with detailed information to resolve the issue. Thorough testing is also vital. Simulate high-load and concurrent scenarios during your testing phase. This will help you expose deadlocks before your software goes live. Use tools that can consistently reproduce deadlock conditions for effective debugging. By combining these strategies, consistent lock ordering, minimizing lock scope, using avoidance algorithms, implementing timeouts, adopting modern concurrency tools, and employing advanced debugging techniques, you can effectively prevent deadlocks and master the art of debugging in complex software systems.